Hi, I'm Alex.
I'm Wolf. We're both data scientists at Microsoft with the analysis and experimentation team.
And here in EXP, our mission is to help accelerate innovation through trustworthy analysis and experimentation.
One common problem we tackle in our paper is how to compute percentiles, especially their variance. It's fairly straightforward to compute the percentiles themselves for metrics, but it's a little bit trickier to compute the variance, especially if the analysis unit is different from the experimentation unit. In our case, for example, we want to compute the 95th percentile of a page load time on a website, but our experiment is actually user randomized. Currently, the state of the art involves one of two methods. Either we use Bootstrap, which gives us good results for large n, but is very costly because we need to compute hundreds and hundreds of percentiles to get the results there. The second approach would be to use an analytical method using density estimation, which is less computationally expensive, but actually a hard problem in and of itself. And also we have an additional problem because these density estimates tend to be very noisy, especially near the end of the tail, which is what we're usually interested in, which means that our metrics will also be very noisy. To solve this, we propose a new algorithm that combines the best of both worlds here, which only requires computing 3 percentiles and 1 additional pass over the data, and thus is both accurate and computationally efficient.
Another type of problem we face from time to time is within subject analysis or longitudinal analysis. Suppose you're tracking a metric over time. Let's call it this xt. And you're wondering, is this dip is a real drop or is it still within the noise range? To answer this question using statistical analysis requires us to understand the whole joint distribution of these time series. In particular, all the pairwise covariance between the two adjacent metric values, using all the data underneath these metrics. Similarly, in online experimentations, we run an experiment over multiple stages. In a crossover design, we start with two groups, group 1 and group 2, assigned with treatment A and B at first. At the second stage, we're going to swap the assignment of group 1 from A to B, and group 2 from B to A. In both of the groups and both of the stages, we have a metric of interest, so we observe 4 different metric values. The analysis of this experiment requires us to understand the joint distribution of all these 4 metrics. The common challenges of these two problems is calculating the covariance and understand the joint distribution are not trivial. Why is that? If we want to compute the covariance between two random variables x and y, we need to observe samples of complete pairs xi and yi. In our case, we have a lot of missing data. That is because some of the users appears in the first period, they don't appear in the second period. And there's certain users appear in second period, don't appear in first period. So we need a way to compute these covariance metrics without assumption of how those data are missing. And for sure, we know they're not missing at random. Turns out, problems like these all can be solved by a fairly classical statistical method called the delta method, which is what our paper is about. In the paper, we provide both the classical applications, novel ideas, and practical guidance on how to apply the delta method to real-world problems.
If you're curious how to solve these and other problems, please be sure to check out our presentation.